Hello everyone. Today we are going to listen from an expert who is doing seismic investigation day in, day out. That is Dr. N. Satyavani, scientist from National Geophysical Research Institute of CSIR. She has completed her PhD in the field of geophysics in 2002 from Andhra University. Since then, she is working with the premier organization, National Geophysical Research Institute. She is an expert especially in common depth point shooting of seismic reflection method. She has done surveys using seismic methods in different parts of the country, and she is an expert in seismic data processing too. So let us hear from her. Thank you so much.
Yeah, good afternoon. My name is Satyavani. I work as a senior principal scientist in CSR NGRI located in Hyderabad. Now here I am giving you a very brief introduction about the seismic exploration. What are the basics that are involved in the exploration? How we are able to acquire the data? What are different modes of acquisition? And how will the acquired data look like, and what is to be done to the data which is coming from the field so that we can get some meaningful interpretation from the data sets. And then I will also show you some different applications of of seismic methods in different scenarios. Okay, and within this entire presentation, there is a one very big uh, package, which is data processing, which itself is a very big subject in itself. So in this presentation, I will just give you a brief of that. I'll not get into the details of the seismic processing and associated steps. It will just be a simple run through of the processing part. My idea is to convey what seismic can do, what is that we can infer from the seismic data. Therefore, I'll try to concentrate more on the images and how we can interpret the seismic images. With this, we'll start the presentation. Now, coming to the basics of the seismic method or seismic propagation itself. Seismic is nothing but but one kind of mechanical wave. It's a sound wave which will travel through the earth, so that we can, when it travels through the earth, it will pass through various layers and it will bring the information pertaining to that layers into the surface, into our recorders. Okay, so now the mechanical waves are essentially of two types: longitudinal waves and transverse waves. Like longitudinal waves, the wave propagation is in the direction of the movement itself, whereas in the transfer movement of the particles, whereas in the transverse wave, the wave propagation is perpendicular to the particle motion. Other way of looking at it is called the other way of looking at this is body waves and surface waves. Body waves are the waves which travel through the body of the earth, through within the earth. So they are the P wave and S wave, that is a longitudinal wave and the transverse wave. Coming to the surface waves, these are the waves which travel in the topmost layer of the earth. That is where the topmost surface, that is why they are called as surface waves. And most of the times, these are the waves which cause maximum damage when there are earthquakes. Okay. Now, how does the propagation look like? Coming to the P wave, this is the medium of propagation. This is how the particle is moving, and this is how the wave is also moving. So this is a P wave, longitudinal wave, everything in the same direction. Expansions and compressions both are going in the same direction. When the wave is sitting, there is some compression, then there is an expansion, then there is a compression. So it's in the same direction. Whereas coming to S wave, the impact is the wave propagation, the particle motion is, the wave propagation is in this direction, whereas the particle motion is in the perpendicular direction. So the wave is essentially traveling in a way that is perpendicular to the incident wave. Coming to the Rayleigh waves and Love waves, these are the two surface waves as I have shown here. These are the surface waves which travel right about the surface. The particle motion here is retrograde ellipse. That is what it is called. So when the wave is going like this, the particles travel in a retrograde motion. That is why there is maximum damage by these waves. The love waves are the waves which travel like this along the axis. Although the moment is perpendicular to the propagation, the particle motion is like this. So these are the surface waves. These are the four major types of waves which are considered in seismic studies. Essentially, most of the time, 80% of the time, we talk of P waves, although nowadays lot of work is being carried out on S waves. Rayleigh waves and love waves, these are surface, these are essentially noise when we are talking about the seismic exploration part, which are kind of unwanted for us. So in the processing part, we try to remove all these surface waves. Now, basic principles, basic physics, which is governing the seismic wave propagation, there are three principles. One is the Huygens principle, the other one is the Fermat's principle, and the most important one is the Snell's law. What are these principles? What does it say? Coming to Huygens principle, it defines the geometric construction to determine the new position of a wavefront at any instant. What it means is when there is an incidence, the wave propagation, there is a wave propagation here. This is the initial wavefront. Okay. Every point on this wavefront will serve as a source for a secondary wavefront. So this will be like this. This was the initial wavefront, and these are the secondary wavelets. Now they form another wavefront. Now again, the points on this, it's like a circle here. This will again form a third wavefront. It is like this. To explain it in a simple way, if you just put a stone in a still water, in a bucket of still water, the way the waves are propagating outward from the stone drop is how the waves travel even in the earth. Okay, this is the Huygens principle where it says every point will become a source of a secondary wavelet. Coming to Fermat's principle, this is the principle which says the actual path between 2 points taken by beam of light is the one which is traversed in the least time. In other words, the light beam will take the path in which it can have very least time travel. The smallest time, wherever it can take, it will assess that this is the smallest time travel, it will take that path. That is why it is also called as principle of least time. The path which will take least time is the path which will be adapted by light. This is what is called as Fermat's principle. Coming to Snell's law. Now, this is very important, and this is the law which will explain the movement of seismic waves within the earth and how we can relate these seismic waves to the medium velocities. Okay, now this is the incident ray. As I told, going by Huygens principle, these are all the wavefronts. Okay, this is just for a better understanding, we draw a normal across these wavefronts and we say this is one incident ray. This is just an understanding, but otherwise physically it will be a complete wavefront. Now, when such a ray is incident on an interface, this is an interface. This is a boundary between two media whose velocities are epsilon 1 and epsilon 2. Okay. Now, this is incident at an angle of alpha. This is the incident angle. Now, when the ray is incident upon the interface, some of the energy is reflected and some of the energy is refracted. Okay. This angle of reflection and angle of reflection and angle of incidence are the same, are equal to each other. Alpha I is equal to alpha R. However, the most important or the takeaway is that sine of this incident angle by sine of the refracted angle will generally give the ratio of the medium velocities. So what seismic is interested is in getting these velocities using the incident wavefronts, reflected wavefronts and refracted wavefronts. This is the complete concept on which the seismic studies are based. Now, coming to seismic API. API is the general term which is used by numerous people when they are talking of seismic exploration. What API means? Acquisition, processing, and interpretation. All these three things put together give you a complete information about the subsurface, and therefore it is called as seismic API. Now coming to seismic, now we will actually transit from one part to the other part to the third part. Okay, now coming to the acquisition part. Acquisition, how was the acquisition done? There are two modes of acquiring data. One is land data, one is offshore data. Offshore, by offshore, I mean in the marine environment, in the seas, open seas. This is on the land itself. There are two major geological situations wherein you can acquire seismic data. Now, modes of acquisition. What are different types of acquisition? One is 2D acquisition, wherein the data is collected along a straight line, okay, whether on land or on marine. Coming to 3D. Now, when we say 3D, it is the data which is acquired like a grid, okay, whether it is again in marine or in land, it is acquired in a grid form. 4D is another, is the next advancement of 3D, wherein the same, for example, I have acquired data in 2002 in some survey area X. Okay. Now I reoccupy the survey area once in 2004, once in 2006, once in 2008, depending on the requirement of the requirement of the field of the or the objective of that work. Okay, generally this is done for reservoir studies, wherever there are oil reservoirs, wherever there is hydrocarbon extraction, they try to see how the reservoir has changed after extraction. Suppose I have a reservoir developed in 2002 and then I have started extraction in that. Now I want to see how the reservoir has changed because of the extraction. So then I do it again in 2004. Then I get to see how much change has come, and from that there are other derived parameters which help in the oil industry. Now coming to the practical aspects of acquisition. Now this is the shot. The shot is fired here, and we have receivers at some distance from the shot. This is the reflection. It has come, it has hit the interface, it has gone back to the receiver. So this is the time that it has taken. Fired, came here, went back. So whatever time it has taken, it is marked here. Similarly for layer 2 and this is for layer 2 and this is for layer 3. now we have time here. Time axis is available to us because the receiver is recording the time. But how to convert this time into depth? That is where we need the velocities of each layers. So if we know the depth, then automatically you know that at one particular, for example, say there is a clay layer and sandstone layer or sand layer, whatever. So where is the depth at which that layer is occurring? To know that, we need the time and we need the velocity of the formation. The entire processing is to derive the velocities of these formations so that the user will know where the depth of that layer is. So this is the typical field layout. So these are the shots and these are the receivers. Hit, go back, hit, then this is a direct reflection. This is a refraction, going here, hitting the third layer, coming to the second layer and coming again to the receiver. Now this is again refraction, coming only up to the second layer and then going back. So that's how it is done progressively. Either these are kept stationary and shots are moved, or shots are moved and these are stationary. It depends on the survey parameters. What is the seismic source which can create these shots? On land, it is either dynamite or vibrator. In offshore, mostly it is the air gun. Now, what are the receivers? These are the receivers. Receivers on land are the geophones. Receivers on offshore are hydrophones, which are embedded in what is called streamer. I'll show you. Now, these are the seismic sources. This is the vibrator and this is an explosive. So, to get the source, what this vibrator does, there is a huge plate here. It simply keeps hitting the ground at regular intervals so that there is a mechanical vibration which is created. And where you have, suppose you have geophone somewhere planted here, these vibrations pass through the earth and then they get recorded on the geophones. Okay, this is for relatively shallow targets, maybe up to 2-3 kilometers. Coming to explosives, this is generally for deeper targets. So you just fire a explosive, they dig a hole depending on the depth of investigation or depth at which they want the data. They dig a hole and then they keep the explosive there and they blast it. So the blast creates a vibration which is again recorded by the receivers which are placed on the field. So this is the seismic source on land. Coming to the receivers, how do they live? These are the typical geophones. These are the receivers which record the seismic impulse on land. So these are planted, as you can see, these are just plugged into the soil at regular intervals so that there is when a shot is fired, the recording can be done by these geophones. Coming to marine data acquisition. Marine data, there is a ship and there are receivers which are towed like this, receivers which are towed like this, and these are the sources. So the source is firing, it gets reflected somewhere and then it is recorded here. Similarly, there is a fire, it is recorded at the streamer. So there are two cables which are towed. One is the gun and one is the receiver cable. How will it look? This is the air gun. What it does is there is a piston. It kind of pushes this here and it creates an impulse. That impulse transmits through the water column, enters the layers beneath the sea bottom, and after reflection, those are recorded by these receivers. This is the hydrophone which is here. Because these are in the ship, what happens is this is the kind of cable. You can see each of them here. This is the cable which will record all these, record the impulse which is created by air gun. So to keep it in buoyant, it is kept in a fluid impact and in this tube-like structure. The tube is towed. So it kind of trails the ship. This is how it looks on the ship. They are generally huge. They run into, say, 6 kilometer, 8 kilometer, 10 kilometer, 12 kilometer also sometimes. So you can imagine the level of experiment wherein you have a cable which is running behind the ship for about 12 kilometers. Okay. Now, travel time curves. Now, how do we identify once the data has come? We will have to identify which is the data that makes some sense and which is the data that doesn't make sense. That is, which is the data which can form signal and which is the data which can form noise. Seismic events, the way to understand those things is first to be able to understand what are the kind of events that can come at all at the first place. So the different kind of, and how do we identify them? Yeah, how do we identify them? Basically, depending on the times that they take to come to the receiver. For example, direct wave. This is the wave which is going directly from the source to the receiver. It is not entering any medium. Seedha from source to the receiver. That is a direct wave. It takes very short time. Then we have a head wave. This is a wave which will travel along the interface. It will not come out. Okay, that is called a head wave. And it will travel to very long distance and then at a very far offset, it will come to the receiver. Surface waves, I have already explained, which travel at the topmost layer of the earth. Then comes the air wave, that is the impulse which is created. It will also travel through the air and some part of it will be recorded by the geophone, by the receiver. That is called air wave. Diffraction, these diffractions happen. Suppose there is a very sharp obstruction to the wave travel in the medium, then what happens is the ray which is coming, as I explained earlier, that ray gets distorted, and instead of coming as a direct reflection, it will either take a greater time or a lower time, or it will get a little diffracted. So that is called diffraction. Reflections I have already explained. These are the reflections. Multiple is something. Suppose we have an event which has hit the layer, came back to the receiver, and from receiver again it will go back and again come out. So that is multiple of a reflection. It's like one time it is reflected, 1 into 2 times, 1 multiplied by 2, because it is hitting the same ray is hitting the interface twice. So that is why it is called as multiple. This is how the seismic record in field, the field data will look like this. So these are the first arrivals. I told they are the first ones to arrive because they travel directly. Okay. Now here, these are the reflections. These are the reflections which take this hyperbolic path. These are the reflections. Ground roll is nothing but the surface waves, the air waves, all these things we call as ground roll because they represent the travel very near to the ground or just on the top layer of the ground. So when we do a processing, we need to remove all these ground roll. The ground roll is unwanted signal for us. What we are interested is in the reflection and of some refractions if we are looking for a deeper interface. Okay, so we have to remove the ground roll. Now come, these are the kind of velocities, as I told you. The travel time and the velocities are the distinguishing factors from which we will be able to understand which wave is what. So if this is refractions are generally like this is a direct wave and then this is a refracted wave. So the direct wave is going like this, then the ground roll, air wave. So ground roll, air wave, direct wave. These need to be removed in the processing. Now this is primary because this is what we want to look at. So we will look at events which are like this. But as I told you, if it hits twice, for example, you see this is somewhat this is parallel to this, but at a greater time. So this is a multiple. Generally, it occurs at twice the time. So this is around 1. So this is around 2, 2.1. This will become a multiple. If you have a thing which is parallel somewhere over here, then that may not be a multiple. That can be an event. Multiples generally take at least twice the time of the primary. So now we know which is the region where so from here, now we know which is the region. These are the arrivals which are required. These are the primaries, which are the hyperbolas. And these, the straight line paths. These is the ground roll, which we need to remove in processing. Okay. Now, that is how the data looks. Now, what are the different ways of acquiring data? Okay. There are two different types of spreads. One is called end-on spread. The other is split spread. Split spread means the short point is at center and both sides there is recording. Receivers are there on both the sides. This is split spread. End on is, suppose if I don't have this part, short is here, receivers are here. That means the short is at one end only. We will not have receivers on the other end of the short. That is called as end-on spread. End-on spread will allow us to go into greater depths because we can have the spread like this and this can go very great. But whereas in the split spread, because of the restriction of the number of geophones, it is more useful for shallow targets. End-ons are more useful for deeper targets. Although this is not necessary, this is a general understanding. Split spreads can be used even for deeper offsets. End-ons also can be used for shallower offsets. Every kind of field setup will ultimately depend on the objective of your field. What is the main target that you are looking at? This is the basic scheme of data processing. As I told you earlier, we will not enter into details of this because this in itself is a very big Very big topic. There are multiple PhDs who are working on each of these steps, various modes of applying them, and all that. So now, essentially, it will be in three parts: pre-processing, pre-stack, and post-stack. Okay, the pre-processing stage. The pre-processing stage. This is the stage where the data is retrieved from the field. Now, in the field, we are putting receivers at some standard distance, say 5 meters, 10 meters, then shots at every 5 meter, 10 meter, or something like that. Now, which record is coming from which shot at which position, those things are all done in the demultiplexing, and then we add geometry. That means we tell to the data, or we assign position to the data required. So suppose I have a shot, I am seeing the data as we have seen earlier. Suppose if this is the data, so we have to assign the location to the data, which is the location from which it is coming. That is called geometry. Field geometry put onto the data set is the geometry application part, and this is the most important part of processing, because this will ultimately, if this is wrong, the entire interpretation will go wrong. So one has to be very careful with this step. So we should know when the shot is fired and which are the receivers which have recorded it and what time. All those information is required. Now, coming to editing is supposed to remove some of the bad traces. Suppose the geophone is not connected properly, it is loosely coupled to the earth, then it will not record properly. So those kind of records we have to remove. Now, this is the essential pre-processing step. Coming to pre-stack processing. Whenever the data is collected, there are various factors which also enter into the data, which are like noise. Now, first, for example, amplitude correction. Now, we have generated some signal. It is passing through the earth. So, the strength of the signal will be decreased as it is going deeper and deeper, understandably. So, but it is going to some X depth, and then from X depth, it is coming to the receiver. So, what the receiver is recording essentially is the signal which has also decayed because of the travel, not because of the layer formation. So layer, while we have to retain the layer information, we have to remove the travel path. That is called amplitude correction. Similarly, we have frequency filters. Frequency filters and deconvolution is also a kind of filter which will remove the effect of the Earth's filtering process. Okay, then again we rearrange all of them, put them into CDP domain, and then we carry out velocity. Now the velocity analysis, as I told earlier, we have to get the correct velocities. This is done in an iterative manner. It's a very exhaustive step, but very important step. In this step, we will be able to assign velocities to those primaries, the reflections. Okay, so now we know the velocity of the formation from the reflection which is coming. So we have to assign velocities to each of these reflections, then correct for those velocities. And once the velocities are obtained, we get a stacking. Okay. Then post stack, we do some, once the stacking is done, then we do some migration and some kind of enhancement of signal. Okay, this is the general scheme of data processing. Essentially, there are three steps: pre-processing, pre-stack processing, and post-stack processing. In the pre-processing stage, geometry application and demux is very important. In the pre-stack stage, the filtering and velocity analysis are very important. Coming to post-stack, then the post-processing. In the post-processing stage, we have the signal enhancements, and in the migration, this is a very big subject. This comes up because of the sharp structures. So we have to remove effect of those structures. So this comes in the post-stack processing part. This is how the field record will look. This, for as an example, I am showing data from 3 shots. Okay, the shot point is here, the flag. The numbers that you are seeing are the receivers. So that means if I have 361, 380 over here, so all these 380 are the geophones. So when the shot is fired, then every trace will represent one geophone location. So for the first shot, you have this many. For the second shot, you have this many. For the third shot, you have likewise how many ever shots. Sometimes the number of shots runs into thousands also. So for every shot, there will be a record. So what these is the general field data, how it will look like. While this data in itself does not convey much, we have to do the data processing from the steps that I have shown you. And after processing, we will get sections like this. So these are the sections which will allow us to understand, to interpret what is there. This is a marine data. So this complete thing is water column. There is nothing here. There is no interface. So whenever a shot is fired, it hits and it comes back. So it will always look for an interface. What we will map with seismic is the interface information. So this is the first interface that we got. Then we have the second interface somewhere over here. Then we have some dipping features here. That means the subsurface underneath my survey line is looking like this. This is how we do seismic. While now the ultimate objective of acquiring seismic data is to get sections like this along the profile, which will help us understand what is happening beneath the surface at that particular location. Okay, with this, now we come to the application part of it. Now we know what is seismic, what are the physics that is behind the physical principles, then what is the acquisition, pattern of acquisition, what are the sources, what are the receivers, how they are laid, and how the raw field data will look and how it will look after processing. While this is the complete suite, in a nutshell, this is the complete method of seismic exploration. Now we come to understand what are the applications of this method per se. Okay. Now, while there are many applications, I have just listed out five major applications of the seismic method. First one is subsurface structure. From subsurface structure only we will be able to infer any of these things. Okay, by subsurface structure here, while all these are subsurface structures, this while telling this subsurface structure, I mean a very deeper layering. Okay, now this is one example from the Delhi Aravalli fold belt in Rajasthan. So this is the seismic data acquisition line. Okay, this is a 2D data. I told you 2D data is the data which is acquired along a line. So this is the 2D data. After data is acquired and processed and everything, we get the seismic stack section. I'm sorry for the resolution of this, but this is a very big chart for the purpose of understanding. I've just squeezed it and put it here. So these are some interfaces that we are finding. Okay. From these interfaces, we draw these lines and we get the depth section. So now we have, this is the subsurface section for this complete profile. So the geology of the subsurface under this profile is like this. And this is a very deeper one, which goes up to 40 kilometers in depth. So we are able to image up to 40 kilometers. And these are the structural disturbances which are marked here as faults. Okay, these are coming from features like this. If you can see, these are the features. This complete upwelling thing is coming like this. Okay, this is how we do the seismic study for understanding the geological features and to understand how it has come up over the ages over here. So this is your Delhi fold belt. So there is some kind of compression happening here, and these two faults are causing this upcoming of the entire formation. That's how the fold belt is formed. This is at a very deep scale. Now come to the very shallow scales. This is for identification of hydrocarbon. Okay. Now, hydrocarbons generally get accumulated in situations where there is this kind of fold structure or this kind of fault structure, because when once accumulated, they need a trap, they need a closure. We just don't want them to pass everlasting. They should get trapped at one place, and after getting trapped, it decomposes, and then oil is formed. This is the general understanding of hydrocarbon. So while we are doing hydrocarbon exploration using seismic, we look for this kind of structures in the seismic image. So if we have this kind of structures in the seismic image, so this is an anticlinal structure and this is a fault structure. Hydrocarbon accumulation is coming here, but because this is a fault, it cannot go beyond the fault, so it gets accumulated here. Similarly, even here, it is getting accumulated at the anticlinal part, and because of whence it cannot go down, everything gets accumulated here. So this is the reservoir, because it is able to hold the hydrocarbon. It is called as reservoir, and this is a rock, the source rock. So this is called cap rock because it is capping this formation. It's not allowing the formation to go out, hydrocarbon to go out. So this is the general geological situations where we can expect hydrocarbons. So when seismic, how will it look? It will be like this. Okay. See, this kind of, imagine this one, it will look like this. So you can see this fold kind of structures. So these are the anticlinal structures, and you see these bright spots. It can be a possible formation, hydrocarbon formation. Okay. So this is this now here. This is only up to 3 kilometers. From 40 kilometers. This is a very kind of a very shallow thing. The other major exploration aspect coming to seismic is coal bed methanes. Coming again to the energy scenario, coal formations are generally in very thin parallel layers in the earth subsurface. They form in thin layers. So we have to first map those thin layers to understand where the coal is, and seismics is the only method which can effectively help us first identify where the thin layers are. Now, once we know where the thin layers are, then we can report it, and then there can be some kind of exploration activity. So this is the seismic image. Again, you see these parallel layers, bright layers. So these are formations. Okay. So again, top and bottom of these, if we plot them without the seismic in background, this is how they will look. So once we give from seismic, once we give this coal seam information, then the company will try to drill through these formations and try to confirm the presence of coal in these layers. So once they know that coal is present in that particular seam, then they go for excavation in those seams. So this is generally for coal exploration. Now, coming to the other major, very important and very exciting aspect of seismic is identification of gas hydrate. Now, what is a gas hydrate? Gas hydrate is a crystalline structure wherein the methane gas is present within the void spaces of the water molecule. So we have a water molecule, and there are some open spaces in the water molecule in which methane gas will enter. It will sit in the water molecule, and that will form an ice kind of structure. All this is happening in the marine environment and in permafrost environment. This is not possible in the land because we need the presence of water essentially. So this is essentially in the marine scenario. Now, why is it so exciting? And these gas hydrate will form only in specific temperature and pressure conditions. That means they form this ice-like bodies only in some specific temperature and specific pressure. Why is it very exciting? Because 1 meter cube of such ice, if it can get dissociated, it can result in 164 meter cube of gas and 0.8 meter cube of water. So 1 meter cube can hold 164 meter cube of gas. Just see the ratio. So this number is very exciting, and that is why this study has become very important these days worldwide. Gas hydrate studies are gaining more and more importance because of the huge volume that they carry. Now, how can seismic help in this? Even here, we do a seismic survey. Now, we try to again map the interface. So, this is the seafloor interface, and this is the BSR interface. Now, what is a BSR? BSR is the one which will tell us that there is a possibility of hydrate existence. How do we identify BSR? We try to look at the events which are parallel to the seafloor, like you can see here. They mimic the seafloor. Now, the depth below seafloor based on thickness. So, each area will have a zone where a depth zone where these pressure and temperature conditions are satisfied. So, when those conditions are satisfied, then only there is a hydrate. So, for every region, at least for Indian margins, we have the stability map. Suppose if I go to Kerala offshore, I know whether there is a possibility of hydrate existence, and if it is there, what is the depth window where it can form. So this information is already available. So we have to look for mimicking, we have to look for the depth at which, whether this depth is satisfying that zone or no. And then we have to see the reversal also, see seismic waves. Suppose it is coming like this, it is a peak. At the BSR, it becomes a trough. BSR is nothing but bottom simulating reflector. It is called sea bottom. Bottom simulating is mimicking, reflection is reflection. Okay, so bottom simulating reflection. Similarly, there will be, again, there is a cross cutting. If you see, the general layering is like this in this region. We can see at every place it is like this. However, because the gas hydrate is governed by pressure and temperature, it has nothing to do with the lithology. So it will almost always cut through the general lithology. It doesn't care for the lithology so much as it cares for the temperature and pressure. So that is very important aspect. Now, enhancement. If you see the reflection strength, it is almost comparable to that of the seafloor. Compared to all other reflections, this comes out as the strongest one. So these are the kind of proxies which we look for. Once we have the seismic data, we look for all these things. If all these things are satisfied, then we say, okay, this is the region where there can be possible formation of gas hydrate. Although there are advanced studies, but for a general understanding, this is how they form. The other most important application of seismic nowadays is engineering. This is for the design of infrastructural projects, like, for example, dams, power plants, huge steel plants, and things, and mega infrastructures, even for metro rail tracks, for all these things, to know the surface, so to know the subsurface strength, whether it can really hold that kind of structures or no, whether there is any earthquake hazard in that region or no, if there is an earthquake hazard, whether it will affect this region or all these things are studied much prior to the construction of the project. So this is one such example wherein there is a seismic line and they have acquired data and they processed, and this is an interpret. This is the ground surface, and there are this kind of layers, 2, 3, 4, 5 layers, and this is bedrock. Bedrock is by far the strongest, the very hardest rock on which major structures can be put. So if I want to construct something, then I have to look for this depth of, what is the depth at which this can go. So this is so after interpretation, you will get to know what are there, what is the fine grain deposit. Obviously, in fine grain deposits, you cannot put huge structures. So someone has to go up to this depth. So to do a construction, if you know this bedrock depth, then you will know whether it is feasible to construct anything there or no. So this is another major thing which is being done nowadays. It was there since long, but it has gathered much attention over the past few decades due to the advancement of the methodology, due to the advancement of the instruments and everything. So these are the major applications of seismic. With this, I come to the end of this talk, and I hope I have given you a brief introduction, brief summary, or excited you enough to study seismics. It has very great prospects, and you can actually do wonders if you take this as a career option. With this, I thank all of you, and that's from my side. Thank you all.